Recording is rolling. It's Friday, May 13th, and we're picking up on the quantum mechanics journal at Feynman diagrams. Remember the last couple we looked at yesterday were looking at the standard model of particle physics. There's, well, possibly 17 elementary particles, depending on how you count them. And the last one that was experimentally verified, might say discovered 10 years ago, was this Higgs boson, which is an excitation of the Higgs field, which is what, according to particle physics, gives particles mass or anything mass, right? And therefore inertia a little bit. Right. So Feynman diagrams. This is a diagram come up by this guy, Richard Feynman, that should represent particle collisions. Now there's different kinds of particles, different categories. We're just looking at standard model yesterday. So let me flip the screen over and show you guys some examples of some Feynman diagrams. Oops, let me bump this, close, screen to share. Okay. And right, we're not quite there yet. Feynman diagrams. Right, so I've got this muted. There's a guy like narrating how these work, but I'll just give you guys a quick synopsis and we'll look at some of these. So different kinds of particles. Right, oh, here we go. Right, you guys see how time actually passes forward, moving up this graph, and then to the right is like a spatial dimension, maybe like one axis, something like that. And now here there's two electrons interacting. So how does this work? So we've got two electrons, they interact, and this wavy line here is a photon. There's a diagram somewhere here that will list this out. Right? And then if you, okay, there you go, represents energy exchange. Here we go. So I'm going to copy down that key right there, and also an example of one of these diagrams. So what we got? I know a straight line, we got to call it fermion, which you guys remember from yesterday could be like a lepton or a quark. Right? Those like there's 12 of those elementary particles. Right? That wavy one, photon, which you guys know is like electromagnetism, light, for example. That curly one, gluons, that's the one that has to do with the strong nuclear force, right, that holds all the protons and neutrons together in the nucleus, gluon. Right. And then a dashed line is some other form of a boson. Okay. Right. So there's your main symbols. Now you saw some arrows with that example we're looking at too, right? So, right. You guys got those copied down if you want them, right? And you'll have to exactly what I have on my notes, but that's probably a pretty good key right there, right? Oh, do you guys see how here the arrows are actually backwards of time? See if time is moving forwards, like up the graph. See how these arrows are backwards, right? That means that they're talking about an antiparticle here. Also, it looks like electron, but it's positively charged. That's actually called a positron. So a positron is like an electron, but it has positive charge. It's actually an antiparticle. It's like it's antimatter. If you mix matter and antimatter, well, you get like pure energy. It just annihilates. It creates a nuclear reaction that gives like maximum energy. Okay, so let's look at some other ones. Here's some other Feynman diagrams. Just show you guys some examples, right? And naming them and what, giving you guys a story what they're about. Right. All right. So there's a bunch of them right there. Let me go back to this one. I'm going to copy down that one right there because that one looks like a pretty fundamental example. Right. It's like two electrons interacting. Right. Looks like they're headed toward each other, and maybe they bounce off each other. Some version of that, like release a photon. All right. So I got that copied in my notes. You guys get there? You guys ready for quantum computing? Quantum computing. Okay. This one is developing technologies.
A classical computer performs operations using classical bits, which can be either 0 or 1. Now, in contrast, a quantum computer uses quantum bits or qubits, and they can be both 0 and 1 at the same time. And it is this that gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit: a single photon, a nucleus, or an electron. I met up with researchers who are using the outermost electron in phosphorus as a qubit. But how does that work? Well, all electrons have magnetic fields, so they're basically like tiny bar magnets. And this property is called spin. If you place them in a magnetic field, they will align with that field, just like a compass needle lines up with the magnetic field of the Earth. Now, this is the lowest energy state, so you could call it the 0 state, or we call it, for the electron, spin down. Now, you can put it in a 1 state or spin up, but that takes some energy.
If you took out the glass from your compass, you could turn the needle the other way, but you would have to apply some force to it. You have to push it to flip to the other side. And that is the highest energy state. In principle, if you were so delicate to really put it exactly against the magnetic field, it would stay there.
Now, so far, this is basically just like a classical bit. It's got 2 states, spin up and spin down, which are like the classical 1 and 0. But the funny thing about quantum objects is that they can be in both states at once. Now, when you measure the spin, it will be either up or down. But before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other. Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering 2 interacting quantum bits. Hello, hi. Now there are 4 possible states of these 2 electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 0, 0, 0, 1, 1, 0, 1, 1. Right? There's 4 numbers. But these are still just 2 bits of information, right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write a quantum mechanical state, which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of the system. Whereas here I only need 2. Now, if we make 3 spins, we would have 8 different states. I need to give you 8 different numbers to define the state of those 3 spins. Whereas classical is just 3 bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits in what we call the fully entangled state. So you must be able to create these really crazy states where there is a superposition of all 300s being one way and another way and another way and so on. Then you have like 2 to the 300 classical bits, which is as many particles as there are newtons.
Whoa, whoa. So, got a little bit more to say, but some main ideas out of that. Oh, let's focus here. Here we go. Okay. So, classical computer, you guys know files stored digitally with just a string of 0s and 1s. So every time you type up a Word document and hit save, string of 0s and 1s. If you have a song file like an MP3, if it's digital, it's just saved as much as 0s and 1s. That video that I was playing, right, the whole MP4 with image and and sound. It's just a file, an MP4 file, with just a bunch of zeros and ones. Okay. Okay, so that's all classical computer, right? Now let's just deal with the quantum computing. Now, okay, this is a developing technology. So they kind of got these, but not really. It's not really fully developed. They have not these classical bits, but these qubits that exist in a superposition state where they're both 0 and 1 until, of course, you measure them and they have to collapse to one or the other state. Okay? Where 2 qubits, we say, would contain 4 classical bits worth of information, and more generally, it's 2 to the power of n. Right? So, like 2 to the 2 is 4. So that's how this lines up with this. Right? But then if you have, let's say you had like 300 qubits. Right? Well, if you have 300 classical bits, great. If you have 300 bits of info, great. Zeros and ones, probably create a very tiny file with that. But 300 qubits at 2 to that power, right? Because you have to position, could be 0 and 1 simultaneously. Okay? That would equate to the number of particles in the observable universe. Think of all the elementary particles that make up the atoms that make up you and everything in this room and the entire Earth and our sun and our entire galaxy, and how about all the galaxies that we can see in the observable universe, going all the way to the edge of the observable universe, like the Hubble Deep Field right there on the wall. So that is like 2 to the power of 300. Whoa! So you see how like crazy big these numbers get really fast. Right, so what could these quantum computers be used for? Well, to run things just like a video file or something. They don't really give you an immediate advantage. You're better off just using a classical computer. But if you want to solve some crazy problems where you need like you have like bajillions of possibilities and you have to have a computer go through and check all of them, then that could be something that quantum computing could be used for. Suppose there was like some encrypted like password that was like nearly impossible to track, but again, even though it's like nearly infinite number of possibilities what it could be, but just our human brains would be technically finite, right? 2 to 300, still a finite number technically, right? So this computer could search through and probably solve those kinds of things. All right. So now you guys are familiar with that. Something that's sort of related, because this has to do with like information, right? How quantum mechanics ties to information. Well, this next one does too. And this next one's a really weird one, which I do have a video for. It's kind of long and slow, although really interesting. All these, if you want to search on the internet and find more about these, please do. But I'll go ahead and handle this one myself. Maxwell's Demon and the Landauer Limit. Right. So what's this about? This goes back to a really strange thought experiment in the 19th century. James Clerk Maxwell, we sort of ran into this guy before. When I showed you guys electricity and magnetism, James Clerk Maxwell wrote down 4 very famous electromagnetic equations. They're differential equations, involves some high-level calculus. Einstein, for example, was looking at those equations, and embedded in those equations is an implicit assumption that the speed of light is constant, which kind of baffled people at the time. So it's kind of crazy that came up with these equations at all. But this was one of the inspirations for Einstein to eventually formulate theory of relativity. I'm not talking about this particular example of Maxwell's demon. I'm just talking about Maxwell's equation. So we just give a little bit of historical context. Okay, but around that time, 19th century, electromagnetism is being formulated and set down in equations, and the laws of thermodynamics. I guess remember that really abstract idea of entropy, right? It has to do with I think there's a time order of things in the universe and these thermodynamic processes, right? And do you guys remember the laws of thermo? Right, so the first law of thermo is that energy is conserved within the universe. Okay, so that's all fine and good. Right? We solved lots of energy conservation problems last semester. And then the second law was a little bit more abstract. That's the one that had to do with entropy. Right? Entropy. Right? And entropy, well, there's a lot of implications embedded in that. So to try to strip it down to what's relevant to this particular thought experiment, this crazy thought experiment, I should show you guys. You guys remember if you have 2 tanks of water beside each other? And they're different temperatures. You got a hot one and a cold one. And let's say it's relatively cold, closed system. Okay. Then the hot water will transfer thermal energy to the cold water, and they'll eventually reach an equilibrium temperature. Right? You guys remember that? Okay. So you guys see these 2 tanks next, side by side, right? Okay. Let's look inside these tanks. Let's say they're like made out of glass or transparent. We can see inside these, right? Okay. Now, what you would never expect to see, though, is if you had 2 lukewarm tanks of water and you walk away and come back later, that one tank of water has spontaneously transferred heat energy to the other so that one becomes hot and the other becomes cold, right? Now, in terms of the first law of thermo, conservation of energy, maybe there's technically nothing wrong with that, but the second law of thermo says the time order of that process, that will never happen that way, right? Now you can force it to happen, and that's what refrigeration is, that's what air conditioning is, but it'll never happen spontaneously, right? At least not on the macro scale, right? So that's one of the things that's embedded in the second law of thermo, right? Now Maxwell was thinking about this, and he was thinking, well, I remember kinetic energy theory of temperature. Suppose I have a bunch of molecules in here. You guys see all these molecules floating around? Okay. Maybe it's like 2 tanks of water. So these are a bunch of water molecules. I'm just representing with like these bubbles, right? Okay. And they're all moving at different speeds, but there's like an average speed, which is going to correlate to some temperature. Maybe it's like room temperature. Okay. And suppose you have perched over the top of these 2 tanks a little character. We're going to call this guy a demon. I don't know why. I don't know if there was like a connotation about like something to do with like knowledge he shouldn't have back in the day or something, but I'll draw a little demon character. I'll tell him pitchfork. And the deal with this character is that he has universal knowledge, universal information. And so he knows something about the individual speeds of every single one of these molecules. And he's watching them like bounce around in these tanks, right? And what this guy could do is he could open a trap door, say like right here, open a trap door instantaneously, and allow these particles to pass through one to the other side. And what this guy wants to do is he said, hey, I'm going to let all the fast moving molecules collect on one side and all the slow moving molecules collect on the other side. So if it's fast, he lets it into the left, and you got all these speedy molecules like whizzing around on the left side. Okay. And if it's moving relatively slow, then he lets that into the right side. And if it's already on the right side, then he just doesn't open the door and it stays over here. Okay. Now the opening and closing that door, let's say it's like spring loaded. So whatever energy it takes to open, you just get that energy back when you close it. So there's like no energy lost to operate the door. Right? Okay. So what would happen after he runs this process for some time is that the left tank would become hot and the right tank would become cold, right? Ooh, kind of like a refrigeration process, right? Except that it would take no energy to run this fridge, right? So you could have a refrigerator that requires no energy to run, right? Furthermore, if you let this hot become hot enough, so that was talking about the cold side for the refrigeration. So that's all fun and good. But the hot side, ooh, what if you got this to be boiling and it could turn a turbine, which could run a power plant? What you could effectively do is have refrigeration and also run the entire energy grid without having any energy input. You wouldn't need to have like a lump of coal to do. No, all you need to do is have universal knowledge. Now let's replace this demon with say like a computer or a robot or some kind of system that's keeping track of these molecules, right? And you can make the case that you could run there's something called a perpetual motion machine of the second type. It's not a first law perpetual motion machine. It's not because it's an energy, but it's because you can actually decrease the entropy over time. This actually would break the second law of thermo, wouldn't it? Right? It would. The second law of thermo, by the way, is one of these laws that's almost asking to be broken in a certain sense. So that's the question that's going to precede all this. Okay. Can the second law of thermodynamics be broken? Okay. So James Clerk Maxwell comes up with this thought experiment and says, well, maybe someday people will come up with some technology, like a computer system that could replace this demon character, and you could actually run this whole thing and actually break the second law of thermo. And people were looking at this thought experiment and think, that's a really compelling argument. And we don't quite know the answer to this yet. Now, 100-something years go by and people finally solve this problem. It turns out that actually you can't break the second law of thermo using this method. And the reason is actually something really weird. So this is a really abstract idea. And this gets to the idea about Landauer limit. Okay. So Landauer limit is there is a minimum amount of energy associated with I'll say with 1 bit of information. Okay, so like these classical bits, like a 0 or 1, right? It's a tiny, I got it Googled right here. Let me pull up a number for you guys. 0.0175 electron volts Yeah, I'll even jot that down. 0.0175 electron volts. You could also call that 2.8 zeta joules, so tiny, 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 tiny amount of energy. Okay? And the deletion of that information, information necessarily increases the entropy of the system or in the universe. Okay, so so suppose you had like a computer here in the space of this demon character, keeping track of all the velocity information of all these molecules. Okay, well, that's a lot of information. You probably need something that was at least about the size of each one of these tanks, because we're talking about information on these individual particles themselves. Okay, and in fact, you wouldn't want to store that information forever, because once a particle's been let through, it's not useful information anymore. Okay, so to save space, you want to delete that information, make way for new information, for like new bits to be reported. Okay? But now, this is a really weird thing that happens, is that when you delete that bit of information, that increases the entropy of the universe. And in fact, the increase in entropy of that universe is going to outweigh the decrease in entropy that you get by letting the separation of these fast and slow moving molecules. So overall, the entropy of the universe still increases. All right, guys got that one? Yeah, so really crazy abstract ideas going on there, but fun times. Moving on. Superconductivity. All right, okay. Superconductivity. Okay, so I'm just going to draw a graph for this, and then I'll switch over and show you guys some slides there. Same thing. Okay. So this graph is going to go. I'm going to put resistivity in ohm meters on this axis, although you could do just plain resistance in ohms. Do you guys remember the lab you did a few weeks back that was measuring the resistivity of Play-Doh? It came out to like 0.25 ohm meters. You guys remember that? Get my voltage and current and length of the Doe cylinder, right? Okay. So now this is a material property, okay? And I'm going to do this as a function of temperature. Now, and let's go in Kelvin, like an absolute temperature. So we could take this all the way down to absolute zero if we want to, right? Have zero resistivity here. Now remember, different materials have different resistivity, like copper and aluminum and Play-Doh have different resistivities. Okay? But what scientists notice is that it's actually dependent on the temperature. And so they took room temperature material, whatever material, okay, and then lowered the temperature and measured the resistivity. And it would also decrease. In fact, it decreased linearly for a while, right? So, okay, lower temperatures, decreased resistivity, which actually means that electricity would carry more efficiently in cold wires than hot wires, right? Okay. But then at some critical temperature, something unexpected happened. Now, a lot of science happens this way, is that, you know, you're just like poking around, playing around with things, and then something crazy will happen. Like, whoa, I just discovered something absolutely crazy. And this is one of those absolute crazy discoveries in history. Okay, I'm going to call this T critical. Okay, the resistivity and therefore the resistance of the wire actually dropped all the way to zero, like exactly zero, like zero resistance. Okay? So you could send electricity through what you can send a current through, and it would have no energy loss at all. Like the wire doesn't heat up, and there's no energy loss. Okay? One of the possible implications of this, one technology that could come out of this, is you could have a very efficient energy storage in batteries, where you just have a current running around in a loop in a wire that was at zero resistance, zero resistivity, zero resistance. And you could store that for years and just tap into it when you needed it. Okay. Now, why don't we have anything like that? Well, it has to do with this critical temperature, which is very, very cold. How cold? Well, it depends on what material you're talking about. It's different for different materials. Now, here's where I'm going to switch over and show you guys some slides about this. So, wait for the video. Share screen 2. All right, let me bring these up. Superconductivity. Okay. Start with basically that graph that I just showed you guys. Right. Okay, so this is one particular example of this. Right. And I don't know what material this refers to, but see temperature critical, it's like it's just over 90 Kelvin. Now inside this room right now, we're pretty close to 300 Kelvin. So 90 Kelvin, that's crazy cold. Like the air in this room, I think would liquefy at like 90 Kelvin. That's so crazy cold. Okay. And then here's a different graph showing different critical temperatures for different substances found in time. So it looks like the very first substances that were found to go superconductive, it looks like mercury, Hg, and lead, Pb. And that was in the early 1900s. Okay. Now, look at those temperatures. So we're talking about less than 10 Kelvin. That's crazy cold, right? That's like close to absolute zero. And more recently, let's see, in the 1990s, looks like this substance here was found to go superconductive at, okay, so a little under 200 Kelvin. Oh, and real recently got one over 200 Kelvin. Right? Now, the catch with these top two is that it also says 30 gigapascals and 100 something gigapascals. Okay, so you would also need crazy high pressures to make that work. Okay, so that's one more inconvenience, but yeah, but there's nothing really at room temperature, right? You guys see that? And materials scientists are still hunting around for, is there something that you could have at room temperature or closer to room temperature that could go superconductive? Because you could create all kinds of crazy technologies from that. But yeah, it's one of those forefronts of science. Okay, next one, quantum locking. All right, quantum locking. Ooh, got a fun TED talk lined up for you guys. Locking.
The phenomena you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor.
Ooh, superconductor. Ooh.
Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from.
Ooh, look, it's that graph I just showed you guys that resistance drops to zero below the critical temperature. Ooh, look at theirs. Okay. Zoom forward a little bit here. There's those magnetic field lines being expelled from a superconductor, right? He's got a picture somewhere lined up here. Look at those, look at those. You guys see those quantized field lines? Now, we've drawn magnetic field lines in the past where you guys have seen those. It seems like an abstraction, like, okay, these field lines go from north to south and you can connect them with arrows and the whole deal, right? But in quantum mechanics, they're actually like quantized into individual fluxons, because wave particle duality, right? Right, we're talking about like quantum mechanics, things are like quantized. Right? All right, let's get to the cool demos.
Now, this is not just levitation, it's not just repulsion. I can rearrange the
So we got a few
fluxons,
minutes left.
and it will be locked
Few
in
more
this new
minutes.
configuration, like this, or move it slightly to the right or to the left. So this is quantum locking.
They're 3 minutes early. Ignore them.
Actually locking, three-dimensional locking of the superconductor.
So yeah, see how it's like locked in space? What else is it gonna do with this? Oh, look at that. Ooh, no, fine, saucer. Oh, yeah. right, let me show you guys one more thing here.
correctly, it stays
Oh,
suspended.
oh, look at that. Okay. Again, relative to that magnetic ring, that superconductor that's flying around, and that is a superconducting disk, right? Is locked in place relative to that. Right, so I'll flash this up here. We officially have 2 minutes till the silent bell, but I'll just leave this up here and we'll call this our pause point today.